All right, this first log problem does not happen often. I'll tell you that right now. So here's we have a log with base 3, 5x minus 1, equals another log, base 3, x plus 7. This is an example of a log problem I like to call the category of rejoice and be glad. Because it hardly ever happens, but when it does, rejoice and be glad because it's so simple. Guys, look, if the left side says, hey, I got a log with base 3 over here, and on the right side it's like, hey, I got a log with base 3 over here, what do you think is true about 5x minus 1 and x plus 7? They're the same. Yeah, so that's rejoice and be glad because this is like a problem any freshman could solve, right? Probably, let's hope, right? That any freshman could solve this one. Right? This is easy, easy, easy. So that's why this problem is so simple. It does not happen often, but it is the case. Okay. And if we check it, we put the number 2 back in place of x, right? 5 times 2 is 10 minus 1 is 9. Okay, so if this is a 9 up here, remember to evaluate a log means find the missing exponent. 3 to what power is 9? 2. I do the same thing over here. I put a 2 in place of x. 2 plus 7 is 9. And 3 raised to what power is a 9? 2. So they match up. So this is like, duh. All right. This will not happen on an SAT test. This will probably, most definitely not happen on a test in here. But if I don't show it, then when you see a problem like this in your math homework, it's like, oh, what do I do? People, it's simple, right? Set the two sides equal to each other. All right, now for the problems that actually look like real work. All right, log base 5, here we go. 3x plus 1 equals 2. All right, this looks like a problem you might actually see. And you all have already said, in order to get rid of a log, you're going to have to use exponents, correct? All right. So, again, remember back to that day we took a quiz. They were at about 10 minutes left of class, and I showed you 2 of our first properties about logs. Okay. And we did it the next day as well. All right, and we said, isn't it weird that you can have an exponent that's a log? And we showed a couple properties where we had an exponent that was a log where the bases matched up. And things simplified, right? Kind of, it was one of those things that's like, well, we're going to use this later when we solve. I also want you to think back to what we talked about very first part of class today. That when the bases matched up, we just kind of got rid of the bases and set the exponents equal to each other. Remember that? Like when they both had bases of 2, we just kind of chucked the 2's and set exponents equal to each other. This is kind of like the opposite operation of that. Here we have 2 sides of the equal sign, obviously equal to each other because it says so, right? We are going to make these sides become exponents. That's totally legal. We can make them become the exponents, and we can pick any base we want, as long as those bases are the same on both sides of our equal sign. And I can make those bases be pi on either side. It doesn't matter. I can pick any number I want for the base. But wouldn't it make sense to pick a base that actually helped me to simplify and get to that x? Because right now, I can't get to the x because it's like in jail with the log. What base, what number base would allow me to get into that log? 5, yeah. So remember, if the bases match up, they undo each other, right? They're inverses. So if I had a 5 as my base, right? and I raised it to that power. See, now I have a situation that can be helpful. This was a process we called exponentiating. It was a fancy word for just saying, hey, we're going to make both sides become exponents. Exponents of what? Exponents of a base that matches the base of our log. Because that first property we learned said the bases match up, they simplify. And the left side now is just 3x plus 1. Isn't that nice? And now the right side is just 5 squared, which we all know is 25. And now again, becomes a very easy problem to do. We subtract 1. We divide by 3. And we have our answer. Think it's a good idea to check our work?
Yeah.
Oh, yeah. So go back up. 3 times 8. 24 plus 1. 25. All right, so 25. Log 25 base 5. Is that really 2? Evaluating a log means find the missing exponent. Right? So log 25 base 5 sure is 2. Or you can take out your calculator now that you can evaluate, right? And do log 25 divided by log 5. And make sure it comes out to be a 2. Which one? All right, one more. Oops. One more problem. Here we have log 5x plus log x minus 1 is equal to 2. How is this one any different? We got a plus sign in it, right? We've got 2 parts to this log. Well, this relates back to what we did Wednesday, taught on Wednesday, and then practiced more on Thursday. So what are we going to do? Which property is this? What's this one called? Which property is it called? Go back to your notes. We learned three properties.
What was the third one?
It was called, none of them were called the solving property. We have one called the power property, one called the product property, one called the quotient property. I don't know what part of this looks like it could possibly be a quotient. If you knew the 3 properties, then I would like you to entertain an answer here. If you don't know the properties, perhaps you should sit back and listen to maybe people that know the 3 properties and not just like throw out a guess, because you just slow everything down when you do that. So let somebody who actually remembers one of the 3 properties that has a plus sign in it, and let's talk about it. Which one has the plus sign? The product rule, yes. So the product rule, product is an answer to what kind of a problem? Multiply. So what are we going to do with those 2 parts? Multiply, yeah. So we're going to condense. We're going to write them together. 5x times x minus 1. You with me on that? So that's important. Before you use any type of solving, we always have to condense using 1 log. What's the base of this log? 10, you betcha. If you don't see one written there, it's a common log, and it's understood to be a base of 10. Bases are always written really small, and they're down, right? There's a subscript. All right, so we need to get rid of the log. So we're going to exponentiate. We're going to write these as exponents. So what base are we going to use? 10, you betcha. So here's what you could do. Instead of rewriting the whole thing, you could just put a 10 down here, right? So they look like they're bases raised to those exponents. Completely allowed. If you want to sneak a little 10 in here because you like to have an exponent or like to have a base there, you can write it in. It's not necessary, but of course you can always do that. Now they undo each other, right? And the left side is 5x squared minus 5x. Go ahead and multiply that out. What's the right side? 100. How are we going to solve this? Can't multiply add yet. Yeah, we got to bring the 100 over.
You gotta take that 5 out.
Yep, you're going to GCF first. Yep. Take a 5 out. X squared minus x minus 20. Now multiply add is much easier. Yep, x minus 5x plus 4. Solving, I have two solutions of 5 and negative 4. Does this 5 have anything to do with the solution? Not a bit. Only things that have an x. All right, now, do I just automatically say, oh, I guess I have two solutions? Got to check it. So let's put the 5 in. All right, so 5 times 5, 25. If I take out a calculator, do you think I could get a solution for log 25? I could get an answer there, right? You could take a calculator out and do that? Okay. How about if I put a 5 in for x on the other one? 5 minus 1 is 4. Do I have an answer for log 4? You can put that in, right? Are you with me? If you're not touching your calculator right now, it's hard to tell. But try it out. Put log 25 minus log 4. And see if your answer comes out to be pretty close to 2. Log 25 plus log 4. I didn't mean to say minus if I did. Log 25 plus log 4. Is it close to 2? Shouldn't have put minus in. I meant to say plus. Sorry. It's 2. Okay, so 5 works. Let's see if negative 4 works. Try to put in log negative 20. Just put in log negative 20. Does that work? Why not?
What is negative?
Is it possible that you could take 10 and raise it to some power and ever get a negative 20? No. Yeah, that doesn't ever happen, does it? So be very careful when you get answers. Always plug them in. And it just doesn't mean that the negative answers are wrong, right? You end up with an extraneous solution here. Please make sure you check your answers. Your homework. That is a required assignment. The last required assignment for this chapter, page 505. We're doing the odd problems. The answers are in the back. Please do not try to turn in a list of problems that just have the answers written by it, because I'm going to hand it right back to you. As I know that I'm telling you, this is the only class that I'd have students try to do that. About 3 people in this room would try to do that. No one else would. All right, so listen, 25 to 59, the odd problems. I know it sounds like a lot, but number 1, you do have the answers in the back for you to check. Number 2, it's written on the board. Number 2, once you get down the pattern, it's really quick. It ends up being a 1 or 2 step solving. So you're either changing the bases so that bases match up, and then it's really fast because you drop the bases and just set exponents equal to each other. You're logging both sides using a strategic base log, right? And then you're just going to use the change the base formula in your calculator. You're going to get an answer very quickly. Or you're exponentiating both sides, which means it's a very quick thing. And after the first step, again, it's a 1 or 2 step solving question. So these should go very, very fast.